More than 400,000 years ago, our ancestors first approached fire, realizing that it kept wild animals at bay. Through fascination and curiosity, prehistoric people came up with imaginative means to use fire for protection, heat, light, food preservation, and social gatherings. For most of human history, we have used multiple applications of fire to generate light and heat. But what brought us illumination at the flick of a switch? It certainly wasn't the development of candles. Since the 1600s, scientists and inventors have worked to understand the principles of electricity, making it possible to use it in our everyday life. Today's world, dominated as it is by faster and faster pace of new technologies, is the result of a revolution in physics which started at the end of the 19th century. Maxwell's laws of electrodynamics led to electricity, radios, and television. Thomson's Nobel-winning discovery of the electron led to modern atomic physics and set the stage for the development of quantum mechanics, opening up the era of electronics. New scientific theories, concepts, and discoveries proliferated and brought about cataclysmic transformations of the world at all levels: technological, social, and cultural. Created in 1954 by some of the protagonists of the 20th century physics revolution, CERN carries today the torch of the virtual circle of knowledge and innovation at an accelerated pace. As distant as it might seem from our daily lives, particle physics has always been a trailblazer for disruptive technologies which have benefited society at large. The invention of the World Wide Web, which was the result of the laboratory's unique collaborative environment, is one of the striking examples. The unprecedented scale and technical requirements of the accelerators, detectors, and computing infrastructure needed by particle physicists for their research has constantly pushed the boundaries of technology. The cutting-edge technologies necessary to build particle accelerators have found applications that go well beyond scientific research. Today, there are over 40,000 accelerators around the world. Only 3% of them are used for fundamental research. The rest are in industry or in hospitals to treat patients. The gigantic detectors built by physicists to explore the unknown have fueled new developments in many fields. From medical imaging to security to art authentication and restoration, all the way to space exploration. To cope with the huge amount of data generated by the collisions in the detectors, scientists are constantly pushing the limits of computing technology, such as the grid, a system to share computer power and data storage across computing centers around the world, AI, and quantum computing. The new theories, concepts, and discoveries emerging from current and future research in particle physics will forever feed the virtual circle of knowledge and innovation. This interconnected journey will continue to unfold and is far from over.
Ladies and gentlemen, welcome to the National Library. Welcome to FCC Week. Welcome to our panel discussion this evening, in which we will be talking about some of the smallest particles in the universe and some of the biggest questions in the world. It's so great to see so many of you showing up tonight, and I think we'll have a lot to talk about. We'll be taking questions at the end too, so don't worry, there'll be time for that. My name is Florian Aigner. I'm a physicist and science writer, and I'll be your host for this evening. And I'm excited to be able to welcome a very distinguished panel here. I'll briefly introduce all the people here on stage. We are delighted to have Fabiola Gianotti, experimental particle physicist and a Director General of CERN. Thanks for coming. A very warm welcome also to Ulrike Diebold. She's a professor of surface physics at TU Wien and the vice president of the Austrian Academy of Science, a highly decorated scientist and does exciting research in surface physics. Welcome. And I'm also very happy to have somebody who's not a physicist, but represents the rest of the world in a way. Verena Ringler is an innovator and practitioner in European affairs and diplomacy. So she's not per se a part of the scientific community, but she connects the scientific community to society, to European governance in a lot of very different projects. We'll be talking about that too. Thanks for coming. So in the short video at the beginning, we have already seen a few very nice pictures of CERN, but still we would like to go a little bit deeper, and so I would like to ask Fabiola Gianotti for an introduction into the topic.
Thank you and good evening, and thanks a lot for the invitation to be on this panel and also to introduce CERN. But actually we are going to discuss tonight about the important and the strong relations between fundamental research and society. And this is the reason why I decided to entitle my presentation The Higgs boson and Our Life. The Higgs boson is perhaps the most mysterious, or, well, let's say, is the simplest and at the same time most puzzling object we have ever discovered in fundamental physics. It's very mysterious, it's related to many open questions in our understanding also of the universe, and so it may appear as being something like up in the air, completely far removed from reality. But actually, this little tiny particle has an important impact on our life, and I will try to explain why. So the Higgs boson was discovered at CERN. CERN is the biggest laboratory in the world for particle physics. Particle physics is the most fundamental of all sciences because it studies the smallest constituents of matter and of the universe and the laws of nature at the most fundamental level. What you see here in this picture is a nice view, aerial view of the Geneva region. CERN is based in Geneva. The red line shows the border between France on the top of the screen and Switzerland on the bottom part. You see Lake Geneva, you see Geneva Airport, and the white circle shows the position of the Large Hadron Collider. It's a 27-kilometer ring, 100 meter underground, so you don't see much on the surface. And is the most powerful accelerator ever built by humanity. So, CERN mission is based on 4 main pillars: fundamental research, collaboration, technological development, and education and training, and I will go through all of them quickly, starting with fundamental research. So, what are the fundamental constituents of matter that we study at CERN? These are what we call elementary particles. What is an elementary particle? Is an object that cannot be cut into smaller pieces. So an object that has no substructure. So if you look at matter, the matter we are all made of, so we, human beings, all the objects in this room and the visible universe, matter, we know, is made of atoms. Atoms are not elementary particles because they got substructure. They have a nucleus surrounded by electrons. Nuclei are not elementary because they are made of neutrons and protons, and neutrons and protons in turn are made of smaller objects called the quarks. And as far as we know today, electrons and quarks are elementary particles. They cannot be cut into smaller pieces and are therefore the fundamental constituents of the matter we are all made of, the objects in this room, the furniture in our house, and the visible universe. The Large Hadron Collider allows us to study matter at the level of the quarks. So on physical scales of a billion, of less than a billions of a meter. So this accelerator can be seen as a giant microscope that allows us to study matter at the level of its fundamental constituent. If you want to study a human cell, a top table microscope is enough. But if you want to study objects like the quarks that have a scale is a billion of a human cell, then you need big accelerator because you need to inject a lot of energy into your system in order to increase your resolutions and being able to see the tiniest structure. At the same time, the study of the very, very small allows us to study the very, very big, so the structure and evolution of the universe. Today, we know that the universe had origin some 13.8 billion years ago. We said that the origin was a big explosion called the Big Bang. Actually, this is not rigorous scientifically. What happened at the beginning, there was, the universe started with a state of very high energy density and very high temperature, followed by the very, very rapid expansion, and then followed by a slower expansion. This is what we call the Big Bang. It's not really an explosion, but it's a very peculiar beginning of this, of all of it. At the beginning, the universe was made of elementary particles. They are free state. And then with time, the universe expanded and cooled down, and these particles started to combine with each other to form structure of increasing complexity. So first the quarks to give rise to neutrons and protons, and then neutrons and protons to produce nuclei, nuclei with electrons to produce atoms, and so on and so forth, up to the beautiful structure we see today, stars, galaxies, and planets. And there are two complementary approaches to study the universe and its evolution. One is based on using telescopes on Earth or in space. Telescopes study the big objects, and by looking at the farthest object, they can go back in time. But if you really want to go to the origin of the universe, very close to the Big Bang, you have to use accelerators. And with the Large Hadron Collider, we can go back to up to a millions of a second after the Big Bang, 10 to the minus 12 seconds. What does this mean? It means that the energy that we produce in the collisions of the beams that we accelerate in the Large Hadron Collider, I will show this in the next slide, corresponds to the temperature that the universe had at that time. And so we are able to reproduce the same conditions that characterize the very early universe, and so understand what kind of phenomena, what kind of forces were at play, what kind of particles were produced. And this temperature corresponds to something like 100,000 billion times the temperature in this room. So we are able to produce a very, very high energy density on a very small space. So the universe, as I said, expanded, and today has a size of 10 to the 28 centimeter, 10 with 27 zeros. It got 2 trillion galaxies. Each galaxy has more than 200 billion planets, so our little and beautiful planet Earth is only one of zillions of objects in this immense universe, which, as I used to say, also put our human concern, worries, disputes into perspective. So how do we do this? We need three main instruments. We need particle accelerator, we need particle detectors, and very powerful and big computing infrastructure, and we need to develop a large variety of cutting-edge technologies across a broad spectrum of areas and domains, and I will come back to this later on. So again, you see here an image of the trace of the ring of the Large Hadron Collider, now in yellow. What we do is to accelerate two beams of protons in the two opposite directions of the ring, up to the highest achievable energy, where the limits only come from the available technology, and in particular technology of magnets, because you need very strong magnetic fields to bend the very high energy protons and to keep them on the circular trajectory. So operation started in 2010, and a couple of years, so first of all, let me say that these two beams collide at 4 points of the ring, where in 4 big underground caverns we have installed 4 big instruments. They are called particle detectors. Their names are ALICE, ATLAS, LHCb, and CMS, and their task is to detect the results of the collision. In this collision with very, very high energy beams, you produce thousands of particles, and so these detectors in principle reconstruct almost every single particle produced in the collision. They are able to identify this particle, to measure the energy, and so to give us a complete picture of the collision event. So if the accelerators can be seen as giant microscope, the detectors can be seen as giant 3D cameras that take picture of the collisions of the beams, and then based on these pictures we can interpret the collision event and try to understand what happened, what kind of particles were produced, a Higgs boson, a W boson, or something else. But the point is that the two beams of protons collide 40 million times a second. So this gives you also another idea of the challenges, and because the detector has to be extremely fast in order to take this picture, analyze them, and then decide whether they want to write them to storage for further analysis or reject them. So we started operation in 2010, and in 2012, ATLAS and CMS reported the discovery of this new particle, the Higgs boson. As I said, a very special one. I will come back to this later on, but I would like to emphasize already at this stage the first link of the Higgs boson with our life. The Higgs boson is related to the mechanism that allowed matter, the matter we are all made of, to form in the initial universe, some 10 to the minus 12 seconds after the Big Bang. In other words, without this mechanism, we will not be here. So it's quite important, an important role. So this is a spectacular image of the underground tunnel of the Large Hadron Collider, 27 kilometers. These blue tubes contain very powerful superconducting magnets. The construction of this, the development first of all, and then the construction of these superconducting magnets is the single most important element that has allowed us, CERN, Europe, to make a big jump in energy compared with the previous collider. This was a collider in the United States, and therefore to bring leadership in high-energy particle physics from the United States to Europe. And these magnets, which were really new generation magnets when they were built in the years 2000, have been first developed at CERN through prototypes, and then the technology has been transferred to industry. They've been built by 3 leading firms in Europe, Alstom in France, Ansaldo in Italy, and Babcock-Knoll in Germany, and the construction of the superconducting magnets for the Large Hadron Collider, again, an example of advanced technology, is a very good example of the collaboration between fundamental research and industry. I would like to spend a few seconds, I guess we will come back to this later on in the panel, but fundamental research is the driver of innovation, simply because very often the technologies we need at a given moment in time do not exist already in industry. So we have to develop this technology in the lab, at CERN in this case, very often in partnership with industry, the most promising firms in the field, and then once the technology is mature, it's transferred to industry for the construction of the thousands of components of a 27-kilometer ring. And so the relation that CERN has with industry is not just a relation of supplier, client and supplier. It's a real partnership where we develop, we do R&D and development together, and then this allows then industry to master the technology and then to be able to build the components we need, but also to open new roads of developments also for their business. This is the tunnel, and this is ATLAS, the largest of the 4 experiments, so it's also, you know, a marvel of technology. You see here the size, you see a human being here on the forefront, and you see how big ATLAS is. It's more than half Notre Dame, the cathedral in Paris, but underground. I find that our instruments, although they have not been built for to be beautiful. They've been built to be to be efficient. They have some aesthetical component. Look at the beauty of this object. And actually, not only me who is saying this. Look at this. This is a opera by French composer Hector Berlioz, Le Troyen, which was on stage in Valencia in 2009. Do you see any similarity? And I can tell you that Atlas was built before so they copied us. But anyway, it shows how science and technology can inspire the arts. So a few more numbers to impress you. The proton beams are are made of a lot of proton. They are very intense. So when they circulate in the ring, there are something like 200,000 billion protons per beam. They travel very close to the speed of light, so they make 11,000 turns of the 27-kilometer ring a second, and there is a lot of energy stored in these beams, 400 megajoule, which I'm told, I didn't measure it, but corresponds to the energy of an Airbus 320 at 110 kilometers per hour. So you have to control this beam with very high precision because they bring a lot of energy. Now, in order to address and solve these technological challenges, CERN needs to develop a huge number of technologies across many, many fields that go from superconducting magnets and materials to robotics, from electronics to vacuum, cryogenics, big data, artificial intelligence, etc. And these technologies have a huge impact on society and are transferred to society at no cost, with no profit for CERN. And this is because CERN embraces and promotes open science. And actually, our funding convention clearly states that whatever we develop at CERN, all our results must be made available to humanity with no profit. And the application to society I'm going to show here, these are just a few examples, are the second element of impact of the Higgs boson on our life. In order to be able to discover the Higgs boson, we had to develop cutting-edge technologies, and now societies benefit from them. You have seen in the movie The Web, which was developed at CERN in 1989. Another example are the use of accelerator to accelerate protons and light ions, like carbon ions, to treat cancer with an approach which is complementary to the standard radiotherapy. Because beams of, for instance, of light ions are much more focused, so they just hit when you target a tumor, they just hit the tumor and do not spread around it, as is the case for the radiotherapy. You can see also a very detailed and very precise high-resolution scanner of the wrist made with CERN electronic, colorful, three-dimensional. See also on the bottom right part of the screen, you can see the deployment of artificial intelligence technologies developed at CERN to the autonomous driving of cars. We have a collaboration with Volvo. And another example, very good. And the other example on the bottom left, you can see cables. These are superconducting cables with very, very small cross-section, just a few centimeters, that are able to carry 120,000 ampere with no losses. If you had to transport this current with normal conducting cable copper, it will have an enormous section of several meters. So this clearly is a breakthrough technology which can be used for the transfer of high quantity of electricity for application to society, data center, or even clean air transportation. We have a collaboration with Airbus with very light cables and without losses. So all this would have been impossible without the vision of our founders. And CERN was founded in 1954, so a very peculiar time in the history of Europe. It was just after World War II. On the initiative of visionary scientists and politicians with two goals. The first one was to reestablish scientific excellence in Europe after the war and counteract the brain drain of scientists that were leaving to the United States in particular. So you see already this very modern vision that the recovery of the continent after the war also requires sustained investment in fundamental research. And this is a very modern and very acute vision. And the second objective was to foster peaceful collaboration between the people and the countries of Europe through science. So the understanding that science is a glue which can connect people in a fractured continent and now a fractured world. 12 European member states signed the founding convention, and today CERN has expanded. And I think the results of CERN, we have a 70 years history, go well beyond the most optimistic dreams of our founders. Not only CERN has become a center of scientific excellence, but has become the world leader in high-energy particle physics and related technology, number one, but also has extended its mission of creating bridges from Europe to the full world. We have 24 member states today, including Austria. We have 10 associate member states from all over the world, including Brazil, India, Turkey, Pakistan. And we have many, many cooperation agreements also with developing countries. We have a budget of 1.2 billion Swiss franc annual budget, which is equivalent to a medium-sized European university. And we have a community of more than 17,000 people from all over the world. More than 110 nationalities are represented, and this community comes from more than 600 universities and institutions, not only from the member states, but also from non-member states, and also from countries that are trying to reduce the gap with the most advanced country. And Austria has a very important participation in all CERN activities. If you look at the age distributions of this population of scientists working at CERN, you see that the peak is 27. So most of the population is young. I'm also 27 years old. No, it's not nice. If you laugh, it means okay. So actually most of the population is made of students and young postdoc. We also have quite senior people coming to CERN every day before 90, 95, which shows that working at CERN increases lifetime expectation. Now, we have a very young population, and training is actually one of our primary missions. And at any given time, CERN is training some 5,000, is a mistake in the slide, 5,500 young people. That is a stunning number. Continuously, we train 5,500 people, including physicists, technicians, engineers across a large number of domains. Typically, 30% of these people stay in research in particle physics. The others go outside, they find jobs elsewhere in society, most of them in industry and other public institutions. And so for me, this is one of the largest benefits, impact of CERN on society, the fact that we continuously provide society with a stream of highly talented young people trained in STEM, science, technology, engineering, mathematics, and we know that society needs STEM talents, and trained in a truly international environment. Maybe one word on science communication. I think that communicating the beauty and utility of science and technology to the general public is very, very important. We cannot think of addressing successfully today's global challenges, from climate change to health, sustainability, without the support and the help of science. And so a few years ago, we decided to build a new center, flagship center at CERN for science, communication, and outreach. It's called the Science Gateway. As you see, it's a building complex with 2 tubes and 3 pavilions. We opened it to the public on the 8th of October in 2023, and since then we have welcomed more than 600,000 visitors from 175 countries. So it's really not just local tourism, and shows that there is a lot of interest in science out there. But of course, the goal of this initiative is to share what we do with the general public, to underline the importance of science, to attract young people to science, inspire them, and to increase the trust in science in today's society, because, as I said, it's very important if you want to successfully address today's global challenges. I have a couple of very simple slides on physics to make explain and share with you a very simple concept. When we look at nature and the universe, they look quite complex. Look at the complexity of plants, animals, human beings, and objects, etc. But at the fundamental level, nature and physics is extremely simple. So in this slide, you can see all the particles we need to explain the visible universe. You can see there are three types of particles. The particles on the left side of the screen, quarks and leptons, these are called matter particles. It's not a very proper term, but the reason is that the particles of the first generation, the up quark U, the down quarks D, and the electrons E, are the fundamental constituents of atoms. You remember I said at the beginning that the atoms are made of quarks and electrons. In particular, they're made primarily of up quarks, down quarks, and electrons. On the right end of the screen, you see the elementary particles that are responsible for the transfers of forces. At the level of quantum mechanics, forces are transmitted through the exchange of particles. So, for instance, the electromagnetic force, which is a very familiar force to which, that we are familiar with in our houses and our day-by-day life, at the quantum level, the electromagnetic force between two electrons is transmitted through the exchange of a photon. And so, likewise, the weak force, which is responsible for the thermonuclear reaction in the sun, is transmitted through the exchange of the W and the Z boson. And the strong force, which keeps quarks inside the nuclei, neutrons and protons, is transmitted through the exchange of other particles that are called gluons. And then you see the Higgs boson. The Higgs boson is in the middle, is separate, is completely different from all other particles. As I said at the beginning, it's the simplest particle. It got no charge. It doesn't have other quantum number or feature of the other particles, just mass. But it brings a new type of interaction. It's not the electromagnetic force, it's not the strong force, it's not the weak force. It's called Yukawa force, Yukawa coupling. So, and it's very mysterious, has this very peculiar role in the early universe to allow matter to form. It may also be related to the fate of the universe, and it is related to some of the open questions in today's particle physics and in cosmology. And so studying the Higgs boson in all details is a must, because it's really a discovery tool. So with this particle, you see just typically 17 particles, so we can explain the visible universe. And now let's look at the equation. These two lines describe everything in the visible universe. There are two types of terms. Those terms describe the interactions of the particle that you have seen in the previous slide through the exchange of the other particle that you have seen in the previous slide. These interactions are governed by quantum mechanics, because small objects, the particle physics, the elementary particles, obey to the laws of quantum mechanics. And then two other terms which describe physics on the large scale: gravity, so Einstein general relativity. So just two lines to describe everything in the universe, from the smallest constituents to the largest one. And by the way, we know now since several decades that physics at the smallest scale, so physics, particle physics, is related to physics at the cosmic scales. I found also, maybe you don't share my opinion, but I find this equation to also be beautiful mathematically. And I would like to report a famous quote of British physicist Paul Dirac, Nobel laureate and one of the fathers of quantum mechanics, who said, "A theory with mathematical beauty is more likely to be correct than an ugly one." So again, there is this principle of beauty in the way nature works at the most fundamental level, and I find this equation to be particularly elegant in their formulation. So, what's next? We've discovered the Higgs boson. We know the elementary particles that describe the visible universe. And I would like to introduce this with this beautiful image of the sky taken by the James Webb Space Telescope. And when we look at images like this one, of course, we are all fascinated by the luminous object, stars, galaxies. But for me, as a particle physicist, like for astronomers, cosmologists, the most intriguing thing in that image is the dark and the vacuum. We don't understand the dark universe, and we don't understand the vacuum. So let me say a few things about the dark universe and the vacuum. 95% of the universe is not visible. As I said, I talk about the visible universe. If you take all the visible objects, stars, galaxies, planets, etc., and you add them together, this accounts for only 5% of the universe. Only 5% of the universe is made of the matters we are all made of, chemical elements, atoms. The rest is made, 95%, is made of forms of matter and energy that we do not understand, and for this, well, we call them dark matter and dark universe. Dark indicates that we don't understand them, but also they do not interact with our instruments, otherwise we will see them, and so we deduce their existence from indirect proof. So this is the darkness, the dark universe. So that's why this is what we have to, the next frontier. And the other thing is the vacuum. The vacuum is not empty in physics. It's full of many things. It's full of particles flashing in and out. It's full of energy. And we don't understand its structure. You could say, who cares? But we should care because actually the vacuum is, we think that the energy of the vacuum is responsible for a current accelerated expansion of the universe. I said at the beginning that the universe had origin from an initial explosion, although it's not really rigorous, and then it expanded, it cooled down, and many bodies were formed, stars, planets, galaxies, and of course you know that these bodies interact through gravity, and gravity is an attractive force, so you will expect that at some point the universe will implode. Is what called at the end, it's called the Big Crunch. But actually about 5 billion years ago, the universe started to expand again at an accelerated pace, meaning that every point in the universe is pulled apart, is pulled away from the other one at an accelerated pace. And we don't know why, but we think it's the energy of the vacuum that counteracts and takes over on and dominates on the attractive force of gravity. So to address this another mystery, CERN has been, started to think about the next big project. And we have just completed the feasibility study of what could be the next project at CERN after the Large Hadron Collider. It's called FCC, Future Circular Collider. I told you the LHC has a circumference of 27 kilometers. FCC will be a 90-kilometer ring. And it could, if implemented, is not yet approved, but if approved and then built, it could become the most extraordinary instrument ever built to study the laws of the universe at the most fundamental level. Technologically very ambitious. It will allow us to push technologies in many fields and also with potential application to all the important fields of society, from health to the digital, energy, etc. The project may be approved on a time scale of 2028, construction start in 2033, and the first stage operation to study the Higgs boson in all details may start in 2048. China is considering building the similar projects, so if you want to keep world leadership in particle physics and related technology in Europe, we should really try to go ahead. And we are here in Vienna this week because the international community working on the Future Circular Collider is meeting here in Hofburg, and we are very, very happy to be here in this beautiful city. Austria has a strong tradition in particle physics, became a member state of CERN in 1959. Two of my predecessors actually are of Austrian nationality or origin. And university and institution in Austria participate not only in the LHC experiments, but in the broader CERN scientific program, which I didn't have the time to explain. Austria has also been supporting a very successful PhD program at CERN, from which many, many talented physicists have been, raised and have now become project leaders or great scientists. And Medostron is an example of application of what I was saying before, the use of accelerators to treat patients with light ions, for instance. One of the two installations in Europe is in Austria, the other one is in Italy. So, in conclusion, what is CERN today is a great success of Europe, is of course scientific excellence. We do have the world leadership in our field, is a driver of innovation for the technology that we develop, is an example of collaboration across borders, and also an example of how to manage and how to govern a big institution with many people from all over the world. And so this is also called CERN model, and more people are thinking of using the CERN model for other fields of humanity, from health to climate change or AI. And it's an example of open science as a means of boosting science. You boost science if you share your results with other scientists, of spreading the benefits of science, and also reducing the inequities across the world. So CERN is not just a scientific excellence. In my opinion, it's a value system, and is a great asset of humanity, and now we are working to ensure a brilliant future to this unique institution, global institution, but European in character, that serves knowledge and society. Thank you.
Thank you for this great introduction. I remember very vividly the fateful day in 2012. The physics community knew something was happening at CERN. There was a big announcement for a press conference, and then we were sitting at the Austrian Academy of Sciences, me and a lot of particle physicists, and we were watching the live stream, and then you came up and presented the new data from Atlas. And then it was announced that indeed this boson that everybody had been hoping for was indeed found. Peter Higgs was in tears. It was a very emotional day. So how do you remember that day? Was this the most important day for you? And was it something that you would maybe have hoped for or dreamt of at the beginning of your physics career?
Well, you know, it was perhaps the most, the best day of my professional life, for sure. It's not, you don't discover a new particle every day, but also this was, I try to explain, it was a very special particle. It was a key object to find, to understand a certain number of open questions, and of course it was also the culmination of the work of thousands of physicists, engineers, technicians had been worked for decades to build this fantastic accelerator, the detectors, the computing infrastructure. So it was really an immense collective effort. And of course, the day of the announcement followed 4 weeks of high pressure, high tension, lot of checks, because we saw the signal of these new particles in our data. But of course, the discovery was announced by 2 experiments, Atlas and CMS, and we both had something really great. But you know, before going public with the discovery, you do thousands, billions, trillions of cross-check. So we were under an immense pressure. And so then the day of announcement was, you know, the big emotion, and you know, it was like it was so much expected. I mean, although there were actually, strange enough, not many leaks, so people were expecting something, but not clear what. So there were young people camping outside CERN auditorium. It was like a rock concert, you know, and to get a seat in the auditorium for the announcement. It was a great day.
Ulrike Diebold, you're also working with particles, but with different kinds of particles, with atoms sitting on surfaces mostly. But it's all quantum physics in a way. Yeah? So we are celebrating 100 years of quantum physics this year, because 100 years ago, major discoveries were made by Werner Heisenberg and Erwin Schrödinger. But back then, physics was quite different. In a way, I have the feeling it was much easier to do physics back then. There were people who won the Nobel Prize just by doing pencil and paper physics, and the experiments back then were very much simpler too. Today we need those huge particle accelerators. How did that happen? What has changed since then?
I mean, Science has changed dramatically in the last 100 years, as has society. But I think we can still do really, really interesting physics, not so much with pen and paper anymore, at least you need a computer, right? But also with more tabletop physics. So my research is, I saw this wonderful, you all saw this wonderful plot of, going from matter to atoms to eventually quarks. So I'm at the atom level as a kind of design, and I still, if you just talked about wonderful moments in your career, so the scanning tunnel microscope that has revolutionized science and society started the nano revolution. That was invented by 2 people in IBM Rüschlikon. And then when I was a young faculty member, I got my own first microscope. And to this day, I will not forget when I tried to analyze these images, and suddenly I saw the things that people had predicted. And I only saw spectroscopically. This was such a orders of magnitude less expensive, orders of magnitude less impact. But for me, it was a wonderful moment in my career as physicist. So yes, you can still do wonderful physics at a much smaller scale, and maybe not going back to -12 seconds of the Big Bang, but still very valuable. And I think that's also happening today.
Mm. Was this a reason for you to go into physics, hoping for these kinds of discoveries?
My reason I don't know, I was interested in everything. I had a really hard time to decide, and then it seemed easy at school, right? It's easy, right? It's all logical, right? And then I thought, well, if I just train my brain and just look into how things work, then I can do anything afterwards. So that's what I figured. So that's why I got into physics. And then when I started working in labs, then I really realized, oh, that's really fascinating.
Verena Ringler, you're a governance expert, and just last week you were in Albania observing the elections there, so completely different topic, really. But you told me that some time ago you also visited CERN, and that gave you some big wow moments. So what fascinated you so much about that?
Yeah, so thank you so much. I come really, as you say, from the universe of people, not physics. And I am in a field where in European affairs, in governance, in diplomacy, civil society, for 20 years, I've been trying to initiate contact between people from these different worlds so that they can meet, collide, build trust before things go down the drain. And here I stand at the bottom of the Alice experiment of the premises with my hard hat on, and I'm thinking, wow, this is so inspiring for 3 reasons. First, when you deal with the world of the European Union and the big questions of our time, you hear a lot of times that there is a lack of political will, that there is a lack of a budget, and here CERN is a wonderful reminder that the impossible is often the untried. Because CERN was also really, I wouldn't say crazy, but you need a lot of imagination and ambition and audacity to get to that moment in 1955 and to come up with this simple but wonderful convention that is still so alive there, and you feel it. This is science for peace, and they enshrined it in this simple but really beautiful convention, and you think, what you have achieved, me getting butterflies in my stomach and thousands of other visitors, it's huge because I don't need to understand the Higgs boson to love CERN. And the second inspiration, CERN is really a lighthouse of hope. We live in an era where we give very little to our children and to coming generations. Very little certainty, little stability, little reliability, and also little ease, little hope, that lightheartedness, that excitement for the future that you have in some decades. We haven't had that in a long time, right? And in that moment, here is CERN. It was founded as an institution and not as a project for like 3 years, and then you have to rebuild the whole thing because you need to have a new budget cycle and so on. No. And in that sense, it's a lighthouse of hope for future generations because they understand that the adults and the ancestors were giving that generosity, that sort of front-loaded trust to future scientists to build something that they can then bring to life some decades later. And I think the symbolism of this is really, it cannot be overstated, and it should go in every impact assessment of any future project at CERN, that psychological effect that a long-term future project has for the young. And the third moment of wow at CERN for me was that the way it's set up, it's so smart that it really serves as an inspiration also for my field, which I call democracy innovation, for lack of a better word, because my field, you can imagine like the physicists 120 years ago. So it's this moment where it's a couple of explorers and it's still very patchy. And the moment that CERN was opened, the most curious, forward-looking scientists and explorers in physics were brought together. They found that pool to actually bring their whole insights to a new level. And this is what we also need for democracy and the big social questions of our time. So that was massive.
Thank you. Okay, now we are already talking about politics a little bit. We live in politically complicated times at the moment, and we all know that the situation in the USA is somehow complicated right now, which is has been the most important science nation for decades. So I think there are big questions now, and you touched on that a little bit already in your talk. But we in Europe, can we be a scientific superpower? Should we try to be a scientific superpower, and how can we achieve that?
We can and we are. We are, for instance, in particle physics. I think science and technology are fundamental, are the future of humanity, and especially at times where there is a lot of emphasis on defense due to the geopolitical situation, it's very important that we do not lose sight of science, of technology, or the values, the good values of knowledge. Knowledge is an important asset of humanity. So, of the impact that the technological progress can have on for the future of humanity. For sure, Europe can be a superpower of science. It's already in some fields, and I think we have to maintain it. I think it's always important. Science is also, as we said, per se, it's a glue. So, especially at a moment of tension, it's something that allows to keep at least some bridges. So it also has a value, a social, political values of connecting people. And again, we should not forget, because of the immediate challenges related to the social and political situation, that the goal is, at the end, a sustainable future for humanity and the planet. And a sustainable future for humanity and the planet can only be achieved if we pursue knowledge, if we have good values, values of collaboration, values of inclusiveness, inclusivity and diversity, values of working together. The good values must always guide us.
You think that Europe is a place that can attract people from all over the world? That can there be? We are talking about brain drain a lot, and there have been times in which many people from Europe went to the USA. Can this reverse? What do you see there?
I think so, and you know there are many initiatives in Europe at the moment. There have been a lot of meetings, important meetings discussing this. There are many universities in Europe that are trying to attract talents from the United States in particular. I think Europe at the moment has really a lot of opportunities. This is a moment of opportunities for Europe. We may have the impression, actually, that Europe is in a situation of weaknesses and there are other powers in the world, but actually it's a time of opportunities for us, I think. And again, the values of Europe, they are important and they're not so widespread, so we should cultivate it, we should defend them, and I think that they will attract many people.
Mm-hmm. You told me that you were also thinking about Korea and its path when it comes to science and technology. So what can we learn from looking at the other side of the world, to East Asia?
Right, so we had a little conversation before where you asked a very interesting question, because it's our strong belief, and they shared it absolutely, that science and technology and research is the foundation of our wealth and our future. But you asked the question if there's causation or correlation,
yes,
right? That rich countries can afford to do science because they're rich, or is it the other way around, that become rich because we do science and research? And in my function as vice president of the academy now, I meet with many people from all over the world, and I remember this anecdotally, this really interesting conversation I had with the science attaché of South Korea. So South Korea was really, really poor 50 years ago. I mean, it's one of the really emerging countries. And then it started investing heavily in technology and innovation, and look at it now, right? I mean, it's wonderful what the output is. But the interesting part is that this science attaché came to the Austrian Academy of Sciences to specifically learn how we invest in fundamental research, because he said, and that was really interesting, he said that breakthroughs come from fundamental research. And I found it really interesting that the leaders, world leaders in innovation and technology, cutting-edge technology, think about the need to invest as a country in fundamental research, in blue sky research, in addressing interesting questions, just by understanding how the world works, because that in the end gives the real breakthroughs. And I think the leading role that Austria plays in quantum mechanics, or recently last Nobel Prize in this really ultra-fast laser pulses, I think that shows that we invest in the right direction. And I think in the long run, this is really what gives us the edge. And I believe also, coming back to the other question, this is a very important time with the US. Really not nice what happens there with science, really, and research. This could be a real chance for Europe to attract not only people from the US, but from all over the world. The science, why US was so successful, is because they were a magnet for talent, for bright people. If you can do that here in Europe, I think then we really have a really big chance. But it was mentioned, China is on the way of surpassing us. So Europeans have to invest in science and research.
I think that's a very important point. I was always wondering about that, this relationship between fundamental science and applied science. It's very hard. You said you can't have one without the other, and you need this fundamental research to trigger technological development too. So what is your understanding? Why do you think are those two so closely connected? Is that we kind of fascinate young people by doing fundamental science and then make them go into technology? Or is it really the innovations from fundamental science that then are turned into economic revenue, or all of the above?
All of the above, yeah. So for sure, right, you need to fascinate people. And as you pointed out, CERN is a beacon of fascination. That's why people go into science and want to do things. There's a lot of technology that needs to be developed in order to do fundamental science. But it's also the fundamental science itself gives the breakthrough, right? I mean, Einstein more than 100 years ago wanted to know why the speed of light is the same in each direction, and what is the fundamental nature of light. I mean, what kind of a stupid question, right? and now we have the GPS system. With a 1 centimeter accuracy, you know where you are, right? So the addressing these questions can really change the way humanity functions. I think it's both. And on the way, we educate a lot of really smart people, and we have a lot of really interesting, wonderful spin-off, like the World Wide Web that comes out of CERN.
You were talking about that we could possibly harness the work that's been done and the kind of cooperation and collaboration that's being done at CERN for other topics, for other projects. And you were talking about some kind of a civic CERN, that to use CERN as a prototype for collaboration, European collaboration in other fields too. Could you tell us a little bit about that?
Sure. I love this question, Florian, because some months ago I delivered a TED Talk here in Vienna, why we need a civic CERN. And I guess this is also why I am here in this conversation today, because of course my inspirations in the Alice premises back in Geneva didn't stop there, right? I kept thinking, how can we use that spirit and that blueprint also for our world? And I was thinking, okay, here the two questions at CERN are about what's the nature of our universe and what is it made of? And I say, why don't we also ask in a civic CERN, in a sister organization, what is the nature of the universe of people? And what does that universe need in order to solve the big problems of our time? What does that universe of people need to get Europe to climate neutrality, to build trustworthy AI systems, to ensure, safeguard, and further develop the peace? Because we don't have anything like that. We don't have a big civilian, peace-led, applied research, development and practice organization, a kind of one-stop shop like CERN is for particle physics, for all these questions on the universe of people, on how we get to a solution and not just the what. And so when we ask why are we failing on the road to climate neutrality and on AI and on these themes, then here come a number of pioneers and practitioners that are ahead of their time, innovators. Some of them work under the headline of diplomacy, where they do back channels, safe spaces, peace, reconciliation. Others, like Johanna Meyer, a beacon in social innovation, who is here tonight, I think, who is a professor at the Hertie School, but also the publisher of the journal on social innovation at Stanford, ask about what organizations need to really help solve these questions. And then others again, like Luisa Slavkova in Bulgaria, she does applied civic education, like in the field with the students themselves directly. Or Adrian Ganz in Munich opened the Politiklabor, where he does not family constellation, you know, where you search for questions on the family system, but thematic constellation work, where it's about a spatial planning, conflict, or other things in the city. And then you go all the way to Claudia Schwalic, who has specialized in citizen assemblies. Others do participatory budgets. So there is this big field. And the pioneers and innovators in that field tell us three things. They say, well, it doesn't work anymore that sort of in the institutions, in a ministry, or even in a university or a science organization, we come up with a fantastic idea, with a wonderful strategy or a law, and then we somehow expect society to accept and take and love it. That doesn't work. We can only solve the problems of our time with the people, not for the people. So the pioneers say we do things differently because we are all members of the universe of people. You in science, you in the public sector, you in the citizen world, and everybody also in the business world, and only as a system, as a pool, like we have it at CERN, can we find these solutions. Then what these pioneers also say is we realize that the key variable, the critical variable, the Higgs boson of the universe of people is trust. It's very hard to develop trust, to increase it, and it's very difficult if you lose trust. You can only create trust, however, in face-to-face meetings. And this is why I have been so adamant about these meetings and opportunities in all my life. You cannot email trust, you cannot send it via an Excel sheet. It doesn't work. Edelman Trust Barometer of this year says we are in a phase of grievance, and never before has this fantastic barometer diagnosed such a dire and low level of overall trust in the world. It's a big and wonderful annual study. And the second thing that the pioneers recognize, okay, the key variable is trust, and the key resource in the universe of people is collective intelligence. It has been proven and shown over and over again, and one friend has done a fantastic peer-reviewed anthology. There's also a contribution by me in this book. But it's a Routledge handbook of collective intelligence for democracy and governance. So this is not something very abstract, but we now know that whenever you and you, two people, are brought together in a room to solve a question together, 1 and 1 becomes more than 2. And that's the checkbot if you work that universe of people. Because whenever people walk out of a citizen assembly or they walk out of a participatory budget, not only do you get a better budget, a better law, because it's more accepted by everyone from the beginning. You didn't wait for the yellow vests and for the tractors to show up and for everything to go wrong. Started from the beginning. And you also get people who walk out of this with civic pride, with a sense of agency, with a sense of empowerment. And we know today that any active experience in democracy, in solving a question of your time and your era, makes you automatically less susceptible for conspiracy theories. And pooling all these emerging, incoming insights from many corners of Europe in a civic CERN and unlocking the universes of people's power is what we would do and what we should do in a civic CERN.
Yeah, so maybe we should learn from what's apparently working very well at CERN and transfer it to democracy, other goals. You were talking about trust, and so what's your impression at CERN? Actually, isn't it amazing that CERN actually works? I've always been fascinated by that because, you know, there is so many people who have to work together in a constructive way. And everybody knows, everybody who's ever organized a big party or something knows it's really hard to get people to work together, and it's hard to get people to trust each other. And quite obviously, it works with great success.
So, you know, I think the secret is the common purpose. There is a purpose, there is a scope that unifies us, and the awareness that individuals, I mean, alone, or not even a single country or a single continent, could reach that goal, and we have to work together across the world. So that's really the scope, and the awareness that we are doing something, I think, good for humanity, trying to push back the limit of knowledge. You know, particle physics is, in my opinion, the modern expression of humankind quest of understanding where we come from and where we are going. So these are the basic questions that have always been with us, with the human being, since we started to, you know, to live on this planet, and these are great questions. These are inspiring questions and difficult questions to answer. So we understand that we have to work together. We understand that we have to develop technology. We understand that diversity is an asset of humanity. Different ideas, people coming from all over the world with different tradition, culture, etc. They enrich the field. They enrich the way we approach the question, and so it's the purpose.
Mm-hmm. You already talked a little bit about the real-world impacts and indirect benefits of CERN. I guess when you are pitching FCC to politicians, then this is a question you're asked very often. What's the real use we get out of that? And especially when it's such a big project, and of course we could dream up different huge scientific projects too. We could build more space telescopes, space stations, whatever. So what is your answer? What can FCC do what other projects could not?
So first of all, I don't see different projects in science to be necessarily in competition. Of course, they require money and funding. However, I think we have to, we scientists, we have to support sciences and the different approaches, the different experiments, the different, you know, from telescope to accelerator, etc. And we don't have to shoot on each other. I never saw money being taken out of a scientific project to be injected into another scientific project. Usually it disappears from science. So I think it's very important that we all work together, also because, as I showed, for instance, fundamental physics, you know, the questions are so complex that they require different approaches. There is, you know, if you want to study the Higgs boson, you can only produce it with the accelerator. If you want to study dark matter, there are different approaches, accelerator and many other approaches. So we have to work together, and the money that goes to science is a little fraction of the money that humanity, you know, and then governments have at their disposal. So coming now to the FCC, as I said, the FCC, what it will produce? It will produce extraordinary knowledge. That's the first answer. And sorry, but for us human beings making progress in understanding the universe, it's a big thing. It's not just a minimum thing. And then, of course, the technologies we have to develop are unprecedented in terms of superconducting materials and magnets, in terms of high efficiency power sources, in terms of new vacuum technologies, many. Of course, artificial intelligence and computing, big data, etc. So, and this will continue to have an impact on society, and it will have a more and more disruptive impact on society. It's clear that in today's world, it's more difficult than it was maybe 20, 30 years ago to sell the pure knowledge. People want to see the impact of society, but I think the example of CERN are absolutely, you know, they are clear and they are absolutely evident. We are doing, of course, also lots of, you know, socio-economic impact, etc. These are numbers that one can find. But for me, the most important thing is to push back the limit of knowledge and technology, because this is the basis for the future humanity.
Yeah, maybe we should open the discussion up to the audience. We have 2 microphones going around. So, are there questions? There is one here in the very front.
Hi, thank you very much for this platform. What would you like to say to young children like my son here? He's interested in science, yes.
So, you're interested in science? Fabulous. Go for it. It's the best profession ever. It's not easy, okay? It's not fun in the sense of fun, but it's a sense of super rewarding. It trains your brain. You're always surrounded by interesting people. You will go on an adventure that is very rewarding. I think you should go and study science, ideally physics.
Hi, I would like to ask, what are some of the unusual or maybe big ethical questions that are being asked in CERN as an institution?
Sorry, what kind of questions?
Ethical questions.
Ethical questions. Are there ethical questions that can be answered at CERN? Ethical questions.
Not really, but it's true that we try to do our science in an ethical way. For instance, nowadays people talk a lot about artificial intelligence and an ethical use of technology. So, of course, these are concerns that we all have, and we have to be also. We think we have to also to be a model in that, and doing research that is responsible in terms of environmental impact, in terms of the use of technologies. But we are not really addressing any ethical question directly.
Do you have ethical questions that should be asked at CERN? So, maybe. Okay, another question.
Yes, here. Thank you very much for the nice discussion so far. You talked about the synergy that develops by people researching together about their teams and so on. However, the universities are extremely competitive. They are based for individuals to try to be the best. There can only be one professor for many hundreds of students. So is this the best substrate that we can do? Or is there a better way that we can look at from the CERN level how we should make the teaching and the basic
Sorry, it's the acoustics is not great here. But I think the question was about in the humanities, the situation is more complicated, and whether...
No, not at all.
Sorry?
The question is the current system of universities that is very competitive the best approach compared to the CERN approach where you have teams, where you don't have individual power of research, basically?
If universities are competitive, I mean, there's competition, I guess, in CERN as well, right? You want to succeed. The question is how you want to succeed. You want to succeed by becoming really good yourself or by pressing people down? The resources are limited, right? And I think there is always a competition for the best ideas. I think you have to have that, otherwise you will not succeed. But I guess maybe I didn't quite understand your question. And then in CERN, I would assume there's also competition between...
Would you appreciate more competition? Would you like to have a Chinese competitor to rally against?
You know, in our field is competition, but also cooperation. We have 500 Chinese scientists working at CERN. They are developing their projects, and some of part of our people of the CERN community actually serve on advisory committee for the project in China. So we, of course, we collaborate as well, but of course there is also competition, especially now where, you know, there is a risk of losing leadership and at a very delicate moment. It is both as competition and collaboration. I think competition does not means in our field that we are not talking to each other, that Chinese are not welcome at CERN, they work with us. But it's also true that, as we were saying before, there are not so many areas in science and technology where Europe has a world leadership, and I think this is one, and we should maintain it.
Thank you. There is a question here in row 2.
Winfried Mitterhoff, a retired particle physicist. I want to take up a remark from Fabiola. She mentioned how important it is that so many people, thousands of people, contribute to an experiment at CERN. And this is often neglected by the public. So I think one should mention that recently there was a big recognition for those people working in the experiment, and that was the reward of this year's Breakthrough Prize, the Milner's Breakthrough Prize, which is given in 3 categories of mathematics, biology, and physics. And it was given to all the participants of the 4 experiments together, which is a big contrast for the Nobel Prize, which can be given only to 3 people at maximum. And the prize is very prestigious. I think it can be really compared in quality with the Nobel Prize. And I think this reward was, first of all, a very nice recognition, and I congratulate all my colleagues who have participated there for this nice achievement. And second, I must a bit criticize that in the media, the mathematics prize and the biology prize has been broadly covered, and the physics prize was just mentioned. A few thousand scientists at Geneva got it as well. And I think it really deserved much, much more public recognition. This was really, I think, also a breakthrough to recognize the modern way how big science is done. It's not done by 3 people, it's done by thousands of people. I think that was really very, very good to be honored in this way. Thank you.
Thank you all for being here. I have a question for Ms. Gianotti. There's some critical voices that say, okay, we have filled the standard model, we know everything about particles, why do we need a bigger particle collider?
Yeah, so again, the acoustic is very bad, so I pick up the few words and extrapolate. So you're saying the standard model, we know everything in the standard model, why we need another collider? So I try to explain it that actually we know only 5% of the universe. The standard model is a well-working theory, but it's not a complete theory. It doesn't explain everything. It has some shortcomings. And so we are looking, the goal is to look for a theory and for a physics, which is called physics beyond the standard model, which allows us to explain the open question. So, and as I try to explain, the Higgs boson is an excellent discovery tool because it's really a very strange particle. It brings a lot of secrets with it. And so it's by studying the Higgs boson in all details, together with other things, of course, but simplified, we may really get, open the door toward this new physics and answering the open questions.
Thank you.
Okay.
Hello, thank you. So this is not a physics question, but I guess a little bit personal question. So between the awe of the first light when it first started and the joy of announcing the results, there must have been a time when, I don't know, maybe it was a postdoc or a PhD student who saw the first leap, the first point on a graph, and thought to himself or to herself, this is the Higgs boson. Could you describe that? I don't know who did he run out to his supervisor? He sent an email. What was the when it was not yet when it was not proven, but someone knew?
Again, if I understood, because the acoustic is quite, it's not optimal, is not just a person, also because the Higgs boson, the way we see it is through statistical analysis. So we see, for instance, a peak on top of a background, and evidence grows with the amount of data that we analyze and we collect. And again, one of the values of this collaboration and this endeavor that brings together thousands of people is that there is no single person who is doing one analysis. There are teams of analysis working all together, sometimes using complementary analysis, doing cross-check, etc. So it's not something that one person see and say, this is the Higgs boson. It's more a collective, what do you say, intelligence, a collective phenomenon where with time you get more and more evidence that you have something really striking in your data.
So there's not the big one eureka moment.
No. This is the Higgs boson. No, it's a statistical process and requires very sophisticated analysis and groups of people working together, and sometimes also, as I said before, different groups developing different analysis in order to cross-check. It's a good principle of healthy scientific approach.
Right, thank you. Okay, so I think we sort of have to come to an end now. I think that we have some time maybe outside to chat a little bit and answer more questions, possibly, if you stick around for a little while longer. To every one of you, I would like to say thanks for coming. Thanks for your interest in the topic. Thanks for your questions. Let's see where the story goes. Let's see what the next chapters of CERN and science in general will be. Thanks for coming and stay curious.